The James Webb Space Telescope is the most significant advancement in human endeavor toward unraveling the mystery of the cosmos. More than just a telescope, James Webb is humanity's most potent eye in the sky, providing the ability to observe the universe billions of years back and hopefully unlock the key to the cosmos's evolution and provide answers to some of the most fundamental questions asked by humanity. But when James Webb used its powerful and sensitive infrared eye to peer back into the beginning of times, what it unveiled was nothing short of revolutionary and potentially catastrophic for our understanding of the cosmos. The revelations James Webb brought forth would set the scientific community on edge, igniting fierce debates and existential questions about the very fabric of our universe.
Thing is wrong. We may have to revise our theory of the creation of the universe.
Join us as we dig deep into what James Webb really saw at the dawn of time. To understand what James Webb is seeing, we first need to revisit the concept of the beginning of time as described by the Big Bang theory. According to this theory, the universe began as an extremely hot and dense point, often referred to as a singularity, approximately 13.8 billion years ago. This singularity contained all the mass and energy of the universe in an infinitesimally small space, and for reasons still not fully understood, it began to expand. This expansion marked the birth of the universe, as space itself began to stretch, and time as we know it began to flow. In the first fractions of a second after the Big Bang, the universe underwent a rapid expansion known as cosmic inflation. During this brief period, the universe expanded exponentially, smoothing out any irregularities and setting the stage for the formation of galaxies and large-scale structures. As the universe continued to expand and cool, energy was converted into matter through processes described by quantum mechanics and Einstein's theory of relativity. In the first few minutes after the Big Bang, conditions were right for the formation of simple atomic nuclei, primarily hydrogen and helium, in a process known as nucleosynthesis. These elements would later serve as the building blocks for stars and galaxies. As the universe expanded and cooled further, gravity began to take over, pulling matter together to form the first structures in the universe. Small density fluctuations in the early universe, amplified by gravity, led to the formation of dark matter halos, within which gas could cool and condense to form stars. These early stars, known as population 3 stars, were massive and short-lived, playing a crucial role in enriching the universe with heavier elements through supernova explosions. Over time, these stars began to cluster together under the influence of gravity, forming the first galaxies. Galaxies are the basic building blocks of the universe, vast systems containing billions of stars along with gas, dust, and dark matter. The formation of galaxies was a key step in the universe's evolution, as they provided the environments in which stars could form, evolve, and die, creating the complex chemical elements needed for planets and life. In the centers of galaxies, clouds of gas and dust collapsed under gravity to form stars. Around some of these stars, the remaining gas and dust coalesced to form planets. Our own solar system, for example, formed about 4.6 billion years ago from a cloud of gas and dust left over from previous generations of stars. The Sun formed at the center of this cloud, with the remaining material forming the planets, moons, asteroids, and comets that make up our solar system. But while most of us strongly believe that the Big Bang is the best way to explain how the universe started and how it changed over time, the fact is that this model, while powerful, does not provide a complete account of cosmic history. Instead, it leaves unanswered questions about the nature of dark matter and dark energy, the asymmetry between matter and antimatter, and critically, the details of the universe's dark ages, the period after the Big Bang, but before the first stars ignited. One of the most significant gaps in the Big Bang theory involves the formation of the first stars, known as population 3 stars. The formation of the first stars marks one of the most significant epochs in cosmic history, the transition from the Dark Ages to a universe filled with light and structure. This event, known as cosmic dawn, is shrouded in mystery, primarily because the first stars are thought to be fundamentally different from the stars we observe today. The first stars formed from the primordial hydrogen and helium gas left over from the Big Bang. Unlike stars today, which form in regions enriched with heavier elements, metals, the first stars were born in an environment devoid of such elements. This absence of metals profoundly affected their formation and characteristics. One of the central mysteries surrounding the first stars is their mass. Theoretical models suggest that, in the absence of metals, the cooling processes in the early universe were inefficient, leading to the formation of extremely massive stars, with masses ranging from tens to hundreds of times the mass of the Sun. These massive stars would have had short lifetimes, burning through their nuclear fuel rapidly and ending their lives in violent supernovae or collapsing directly into black holes. Despite their importance in cosmic history, detecting the first stars has proven to be a formidable challenge. These stars formed at such an early epoch that they are extremely distant, and their light has been redshifted to wavelengths that are challenging to observe with current technology. Moreover, because they were so massive and short-lived, they would have rapidly ended their lives in powerful supernova explosions, leaving behind little direct evidence. One of the key challenges in detecting population 3 stars is the sheer distance involved. The light from these stars has traveled for over 13 billion years to reach us, and during that time, the universe has expanded, stretching the light into the infrared part of the spectrum. This means that traditional optical telescopes, like the Hubble Space Telescope, are not well suited for detecting them. However, the advent of the James Webb Space Telescope has provided a new window into this distant past. As the most powerful space telescope ever built, James Webb is equipped with a suite of advanced instruments optimized for infrared observations. This capability is crucial for studying the early universe, where the light from distant galaxies and stars has been stretched into the infrared part of the spectrum due to the universe's expansion. James Webb's design also allows it to peer through dust clouds that obscure many regions of space from visible light telescopes like Hubble. This is particularly important for studying the early stages of star and galaxy formation, as these processes are often shrouded in dense clouds of gas and dust. That's why one of James Webb's primary science goals is to observe the first galaxies and stars, probing the epoch of ionization and beyond. By capturing light from objects that formed just a few 100 million years after the Big Bang, the telescope can provide direct evidence of the universe's earliest structures. This, in turn, will help answer fundamental questions about how the first stars formed, how they influenced their surroundings, and how they led to the complex cosmic web of galaxies we see today. And as expected, since its launch, James Webb has already begun to revolutionize our understanding of the early universe. One of its most significant achievements has been the discovery of the earliest galaxy ever seen. Named JADES GS Z14-0, the galaxy formed at least 290 million years after the Big Bang, and contains stars that have been bursting into life since an estimated 200 million years after our universe began. Spotted by James Webb's Near-Infrared Spectrograph, or NIRSPEC instrument, the mysterious origins and rapid development of the stars has opened up some fundamental questions about how our universe came to be. Astronomers aren't certain when the very first globules of stars began to clump into the galaxies we see today, but cosmologists previously estimated that the process began slowly within the first few 100 million years after the Big Bang. Current theories suggest that halos of dark matter a mysterious and invisible substance believed to make up 85% of the total matter in the universe, combined with gas to form the first seedlings of galaxies. 1 billion to 2 billion years into the universe's life, these early protogalaxies reached adolescence, forming into dwarf galaxies that began devouring one another to grow into ones like our own. But discoveries made by James Webb confounded this view. In February 2023, a group of astronomers analyzing data from the telescope discovered a group of 6 gargantuan galaxies aged between 500 to 700 million years after the Big Bang, that were so massive they were in tension with 99% of cosmological models. The light from JD's GS Z14-0 is similarly puzzling. In the new research, the light detected by NER SPEC finds its origins in an enormous halo of young stars surrounding the galaxy's core, which have been burning for at least 90 million years before the point of its observation. The galaxy is also crammed with unusually high quantities of dust and oxygen, which suggests its history of starbirth and death may be even longer. Interestingly, this finding shows that ultra-bright galaxies in the early universe are not just the product of active black holes greedily gobbling up matter, as is often assumed to be the case. The new observations show that runaway star formation is also a viable explanation for the surprising brightness of these ancient galaxies. So how did galaxies like Jade's GS Z14-0 produce so many stars so quickly? Answers to this cosmic mystery remain elusive, but it's unlikely they will break our current understanding of cosmology. Instead, astronomers are toying with explanations that include the earlier-than-anticipated appearance of giant black holes, supernova feedback, or even dark energy to understand why these ancient stars were able to form so rapidly. Fascinatingly, in addition to discovering early galaxies, James Webb has provided critical insights into the formation of the first stars, known as population 3 stars. While direct observation of the very first stars remains elusive, James Webb has detected signatures of their presence through the observation of early galaxies. The ultraviolet light emitted by these stars ionized the surrounding hydrogen gas, contributing to the reionization of the universe. By studying the spectra of these galaxies, the telescope has identified the chemical fingerprints of the first stars, providing evidence that these primordial objects played a significant role in shaping the early universe. Webb's observations have also hinted at the possible existence of population 3 star clusters, which would be some of the oldest and most massive star-forming regions ever observed. These clusters would have been responsible for producing the first heavy elements in the universe, setting the stage for the formation of later generations of stars and galaxies. Another area where the Webb telescope has made groundbreaking discoveries is in the study of black holes during the cosmic dawn. Supermassive black holes, with masses millions to billions of times that of the Sun, are known to exist at the centers of many galaxies. However, their origins and how they grew so massive in such a short period after the Big Bang have been long-standing mysteries. James Webb has detected signs of supermassive black holes in some of the earliest galaxies, providing clues about their formation. One theory is that these black holes formed from the collapse of massive primordial stars or dense star clusters, which then rapidly accreted gas and merged with other black holes to grow in size. The presence of these black holes in early galaxies also has implications for galaxy formation. It suggests that black holes and galaxies may have grown together, influencing each other's evolution. The intense radiation and outflows from these black holes could have regulated star formation in their host galaxies, shaping the development of cosmic structures. Moreover, data obtained by James Webb also have provided valuable data on when and how reionization occurred. By observing the light from distant galaxies and quasars, James Webb has measured the amount of neutral hydrogen in the early universe, offering insights into the timing and duration of reionization. Interestingly, Webb's findings suggest that rayonization may have been a more complex and extended process than previously thought. Rather than occurring rapidly over a short period, rayonization might have proceeded in stages, with different regions of the universe being ionized at different times. This challenges the traditional view of a uniform, simultaneous reionization and opens up new avenues for research into the interactions between early galaxies, black holes, and the intergalactic medium. What's notable, the insights provided by James Webb are not just of interest to astronomers. They have broader implications for our understanding of the Big Bang theory itself. By providing a clearer picture of the universe's first billion years, James Webb helps fill in critical gaps in our knowledge, offering new data that can be used to refine and test cosmological models. For instance, Webb's observations of early star and galaxy formation challenge existing models of how quickly structure formed in the universe. If star formation began earlier than expected, this could have implications for our understanding of dark matter and its role in cosmic evolution. Similarly, the detection of heavy elements in early galaxies suggests that the first stars may have been more massive and short-lived than previously thought, potentially influencing models of stellar evolution and nucleosynthesis. Moreover, Webb's ability to study the intergalactic medium, the diffuse gas that fills the space between galaxies, during the epoch of reionization, provides new insights into the nature of dark matter and dark energy. By mapping the distribution of this gas and its interaction with early galaxies, the telescope can help constrain models of how dark matter clumps together to form the large-scale structure of the universe. Interestingly, as of now, the James Webb Space Telescope is still in its early stages of operation. In other words, its full scientific potential is yet to be realized. Regardless, the discoveries it has already made are a testament to its transformative power. As James Webb continues to observe the early universe, it will undoubtedly provide more answers to the fundamental questions about the cosmos's origins and evolution. In the coming years, the observatory is expected to make significant contributions to our understanding of exoplanets, star formation, and galaxy evolution, in addition to its work on the early universe. Its ability to observe in the infrared will also allow it to study objects that are currently hidden from view, such as planets forming around young stars or the cores of galaxies enshrouded in dust. Moreover, Webb's discoveries will likely inspire new theories and models, prompting a deeper investigation into the nature of the universe. As we continue to explore the cosmos with James Webb, we may uncover new phenomena that challenge our current understanding, leading to a more complete and nuanced picture of the universe's history. By that time, no doubt, the question of whether it was time to overthrow the government would have been discussed countless times. After all, the Big Bang, as told, despite its success in explaining many aspects of cosmology, is not without its gaps and unresolved questions. These gaps challenge our understanding of the universe's origins and have driven ongoing research and exploration in modern cosmology. One of the most profound issues with the Big Bang theory is its treatment of the universe's initial state. The theory describes the evolution of the universe from a fraction of a second after the Big Bang onward, but it does not extend to the actual moment of creation, nor does it address the cause of the singularity itself. This leaves a gap in our understanding, a gap that science, as it currently stands, cannot fill. At the heart of the Big Bang theory lies the concept of a singularity, a point where the density of matter and energy becomes infinite, and the laws of physics as we know them break down. Singularities are deeply problematic in physics because they represent a breakdown of our understanding. In the context of the Big Bang, the singularity is a point where our current theories, namely general relativity and quantum mechanics, cease to be applicable. General relativity, which describes the force of gravity and the structure of space-time, predicts the existence of singularities under certain conditions. However, These predictions indicate that at a singularity, space-time becomes infinitely curved, and physical quantities such as density and temperature become infinitely large. In other words, the very fabric of the universe would be infinitely warped, and the physical laws that govern everything from the motion of planets to the behavior of subatomic particles would no longer hold. Quantum mechanics, which governs the behavior of particles at the smallest scales, also fails to describe what happens at a singularity. Quantum theories suggest that at extremely small scales, the fabric of spacetime becomes dominated by quantum fluctuations, leading to a highly chaotic and indeterminate state. However, when combined with general relativity, these theories produce nonsensical results, such as infinite densities and curvatures. The existence of singularities in the Big Bang theory therefore suggests that our current understanding of the universe is incomplete. It implies that a more fundamental theory, possibly one that unifies general relativity and quantum mechanics, is needed to describe the true nature of the universe's beginning. In response to the limitations of the Big Bang theory, several alternative theories have been proposed to explain the origins of the universe. These theories attempt to address the question of what came before the Big Bang, or to describe a universe without a beginning at all. One such theory is the idea of a cyclic universe, where the universe undergoes infinite cycles of expansion and contraction. In this model, the Big Bang is not the beginning of the universe, but rather a transition from a previous cycle of contraction. The universe contracts into a singularity-like state, then rebounds in a new Big Bang, leading to a new cycle of expansion. This theory avoids the problem of a singularity by proposing that the universe never actually reaches infinite density, but instead undergoes a bounce at extremely high densities. Another theory is the multiverse hypothesis, which suggests that our universe is just one of an infinite number of universes that exist in a larger multiverse. According to this theory, different universes can have different physical laws and constants, and our universe may have originated from the collision or interaction of two or more universes within this multiverse. In this context, the Big Bang is simply a local event within a much larger and more complex cosmic structure. There is also the possibility that the universe had no beginning at all. Some theories propose that the universe is eternal, with no origin point. These models often involve modifications to the laws of physics to allow for a universe that has always existed in some form, without requiring a singularity or a moment of creation. For example, some versions of quantum gravity suggest that time itself may not exist in the traditional sense at the earliest moments of the universe, making the concept of a beginning meaningless. The mystery of the universe's beginning also raises profound philosophical and theological questions. If science cannot provide a complete answer to the question of the universe's origin, can these questions be addressed through other means? From a philosophical perspective, the question of the universe's beginning touches on the concept of causality, the idea that every event must have a cause. The Big Bang suggests a moment when the universe began, but what caused the Big Bang? This leads to a classic philosophical problem, the problem of the first cause. If every event must have a cause, then what caused the first cause? This line of reasoning can lead to an infinite regress, where each cause requires a preceding cause, or it can suggest the existence of a cause that itself is uncaused, an idea that some equate with the concept of God. Theological perspectives often address the question of the universe's beginning by invoking the idea of a divine creator. Many religious traditions teach that the universe was created by a deity or deities who exist outside of time and space and are not subject to the physical laws that govern our universe. This view holds that the universe had a purposeful beginning, brought into existence by an intelligent and transcendent being. However, the idea of a divine creator also raises questions. If the universe requires a cause, then what caused the creator? Some theologians argue that God is a necessary being, existing beyond the constraints of cause and effect. while others suggest that the nature of God is fundamentally mysterious and beyond human understanding. In the end, the question of the very first beginning of the universe remains one of the deepest and most enduring mysteries. While science has made tremendous strides in explaining the evolution of the universe from its earliest moments, it has yet to provide a definitive answer to what, if anything, came before the Big Bang. The singularity at the heart of the Big Bang theory points to the limits of our current understanding, suggesting that a more fundamental theory is needed to fully describe the universe's origin. At the same time, the mystery of the universe's beginning invites philosophical and theological inquiry, raising questions about the nature of causality, the existence of a first cause, and the possibility of a divine creator. These questions, like the scientific questions, remain unresolved, leaving us with the humbling realization that the origins of the universe may forever remain beyond our grasp. Another significant gap in the Big Bang theory is the horizon problem. According to the theory, regions of the universe that are separated by vast distances should not have had enough time to come into thermal equilibrium due to the finite speed of light. However, the cosmic microwave background radiation, the afterglow of the Big Bang, is remarkably uniform across the sky, with only tiny fluctuations. This uniformity suggests that distant regions of the universe must have been in causal contact with each other in the early universe, which contradicts the predictions of the standard Big Bang model. The horizon problem challenges our understanding of the early universe. It suggests that there must have been some mechanism that allowed distant regions to communicate and reach equilibrium faster than the speed of light would allow. This discrepancy led to the development of the inflationary theory, which proposes that the universe underwent a rapid exponential expansion in the first fractions of a second after the Big Bang. While inflation theory addresses the horizon problem, it is not yet fully integrated with the rest of the Big Bang framework and raises its own set of questions. Closely related to the horizon problem is the flatness problem, another gap in the Big Bang theory. Observations of the universe show that it is remarkably flat, meaning that the geometry of space is close to Euclidean. A flat universe has a delicate balance between the density of matter and energy and the rate of expansion. If the universe were slightly more or less dense, it would have quickly diverged from this flatness, leading to a very different cosmic evolution. The flatness problem is puzzling because the Big Bang theory does not inherently predict this fine-tuned balance. Without an explanation, this flatness seems coincidental, which is unsatisfying to cosmologists. The inflationary theory, again, provides a potential solution by suggesting that the rapid expansion of the early universe would have stretched its geometry, making it appear flat today. However, as with the horizon problem, inflation is an add-on to the Big Bang theory rather than a fully integrated component. One of the most profound gaps in the Big Bang theory concerns the nature of dark matter and dark energy, which together make up about 95% of the total energy density of the universe. The Big Bang theory, as it was originally formulated, accounted for the observable matter and energy in the universe, but did not predict the existence of these mysterious components. Dark matter is thought to be responsible for the gravitational effects observed in galaxies and clusters of galaxies that cannot be explained by visible matter alone. Its presence is inferred from its gravitational pull on visible matter, but it does not emit, absorb, or reflect light, making it invisible and difficult to detect directly. Despite extensive research, the exact nature of dark matter remains unknown. Dark energy, on the other hand, is even more mysterious. It is believed to be responsible for the accelerated expansion of the universe, a phenomenon that was discovered in the late 1990s. Unlike dark matter, which exerts a gravitational pull, dark energy seems to have a repulsive effect, driving galaxies apart at an increasing rate. The Big Bang theory does not explain the origin or nature of dark energy, and its discovery has led to a reevaluation of the theory. These gaps highlight the limitations of the Big Bang theory in describing the full contents of the universe. While the theory provides a framework for understanding the observable universe, it does not account for the vast majority of its energy content, leaving dark matter and dark energy as significant open questions in cosmology. Another unresolved issue in the Big Bang theory is the baryon asymmetry problem. The theory predicts that equal amounts of matter and antimatter should have been created in the early universe. However, our universe is overwhelmingly composed of matter, with very little antimatter observed. This asymmetry is puzzling because when matter and antimatter meet, they annihilate each other, producing energy. If equal amounts had been created, they should have annihilated each other completely, leaving behind a universe filled with only radiation. The existence of a matter-dominated universe suggests that some process must have created an imbalance between matter and antimatter in the early universe. Various theories have been proposed to explain this asymmetry, including mechanisms that involve slight differences in the behavior of particles and antiparticles. However, none of these theories have been confirmed, and the baryon asymmetry problem remains an open question in cosmology. The Big Bang theory provides a broad outline of how the universe evolved from a hot, dense state to its current form, but it leaves significant gaps in our understanding of how the first stars and galaxies formed. According to the theory, the early universe was a nearly uniform soup of particles, with tiny fluctuations in density. Over time, these fluctuations grew under the influence of gravity, eventually leading to the formation of the first stars and galaxies. However, the details of this process are not fully understood. For example, the exact conditions under which the first stars, known as population 3 stars, formed are still unclear. These stars are believed to have been massive, short-lived, and composed almost entirely of hydrogen and helium, as heavier elements had not yet been produced. The formation of the first galaxies, and how they evolved into the complex structures we see today, also remains an area of active research. Recent observations by the James Webb Space Telescope have begun to shed light on these early stages of cosmic evolution. James Webb's ability to observe the universe in infrared wavelengths allows it to peer back in time to see the first galaxies forming just a few 100 million years after the Big Bang. These observations are helping to fill in some of the gaps in the Big Bang theory by providing direct evidence of the early universe's structure and composition. As James Webb continues its mission, it is expected to make even more groundbreaking discoveries that will further our understanding of the early universe. Future observations will likely uncover more about the nature of population 3 stars, the formation and growth of the first galaxies, and the role of black holes in cosmic evolution. James Webb will also explore the transition from the cosmic dawn to the later stages of cosmic history, including the formation of more complex structures like galaxy clusters and the chemical enrichment of the universe. By studying the light from the earliest stars and galaxies, James Webb will help us piece together the story of how the universe evolved from a hot, dense state to the vast, complex cosmos we see today. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. Mercury. The closest planet to our Sun and the smallest in the solar system, is also one of the least understood. Compared to more glamorous planets like Mars, Jupiter, and Saturn, Mercury has received much less attention from scientific study missions. It's slightly larger than Earth's moon, so scientists assumed it was another cold, dead, and dull, cratered world, without much to offer to our understanding of the story of planetary formation. But Mercury also has its own secrets. And now, scientists using powerful telescopes like James Webb have stumbled upon these secrets. They are seeing something moving that they never saw anywhere else. These revelations could lead to crucial missions to reveal a terrifying truth about our universe. Join us as we shed light on some of Mercury's most enduring mysteries. Mercury is the innermost planet of the solar system and the 8th in size and mass. Its closeness to the Sun and its smallness make it the most elusive of the planets visible to the unaided eye. Because its rising or setting is always within about 2 hours of the Sun's, it is never observable when the sky is fully dark. The difficulty in seeing it notwithstanding, Mercury was known at least by Sumerian times, some 5,000 years ago. In classical Greece, it was called Apollo when it appeared as a morning star just before sunrise, and Hermes, the Greek equivalent of the Roman god Mercury, when it appeared as an evening star just after sunset. Hermes was the swift messenger of the gods, and the planet's name is thus likely a reference to its rapid motions relative to other objects in the sky. Even in more recent eras, many sky observers passed their entire lifetimes without ever seeing Mercury. It is reputed that Nicolaus Copernicus, whose heliocentric model of the heavens in the 16th century, explained why Mercury and Venus always appear in close proximity to the Sun, expressed a deathbed regret that he had never set eyes on the planet Mercury himself. Until the last part of the 20th century, Mercury was one of the least understood planets. And even now, the shortage of information about it leaves many basic questions unsettled. Indeed, the length of its day was not determined until the 1960s, and Mercury's nearness to the Sun gave scientists bound to Earth many observational hurdles, which were overcome only by the Messenger probe. Messenger was launched in 2004, flew past the planet twice in 2008 and once in 2009, and settled into orbit in 2011. It mapped the entire surface of Mercury before crashing into the planet in 2015. Mercury's proximity to the Sun has also been exploited to confirm predictions made by relativity theory about the way gravity affects space and time. At first glance, the surface of the planet looks similar to the cratered terrain of the Moon, an impression reinforced by the roughly comparable size of the two bodies. However, Mercury is far denser, having a metallic core that takes up about 61% of its volume, compared with 4% for the Moon and 16% for Earth. Moreover, its surface shows significant differences from lunar terrain, including a lack of the massive, dark-colored lava flows known as Maria and the presence of buckles and scarps that suggest Mercury is shrinking. Mercury is an extreme planet in several respects. Because of its nearness to the Sun, its average orbital distance is 58 million kilometers. It has the shortest year, a revolution period of 88 days, and receives the most intense solar radiation of all the planets. With a radius of about 2,440 kilometers, Mercury is the smallest major planet, smaller even than Jupiter's largest moon, Ganymede, or Saturn's largest moon, Titan. In addition, Mercury is unusually dense. Although its mean density is roughly that of Earth's, it has less mass and so is less compressed by its own gravity. When corrected for self-compression, Mercury's density is the highest of any planet. Nearly 2/3 of Mercury's mass is contained in its largely iron core, which extends from the planet's center to a radius of about 2,100 kilometers, or about 85% of the way to its surface. The planet's rocky outer shell, its surface crust and underlying mantle, is only some 300 kilometers thick. As seen from Earth's surface, Mercury hides in dusk and twilight, never getting more than about 28 degrees in angular distance from the Sun. It takes about 116 days for successive elongations, that is, for Mercury to return to the same point relative to the Sun in the morning or evening sky. This is called Mercury's synodic period. Its nearness to the horizon also means that Mercury is always seen through more of Earth's turbulent atmosphere, which blurs the view. Even above the atmosphere, orbiting observatories such as the Hubble Space Telescope are restricted by the high sensitivity of their instruments from pointing as close to the Sun as would be required for observing Mercury. Because Mercury's orbit lies within Earth's, it occasionally passes directly between Earth and the Sun. This event, in which the planet can be observed telescopically or by spacecraft instruments as a small black dot crossing the bright solar disk, is called a transit, see eclipse, and it occurs about a dozen times in a century. The next transit of Mercury will occur in 2019. Mercury also presents difficulties to study by space probe. Because the planet is located deep in the Sun's gravity field, a great deal of energy is needed to shape the trajectory of a spacecraft to get it from Earth's orbit to Mercury's, in such a way that it can go into orbit around the planet or land on it. The first spacecraft to visit Mercury, Mariner 10, was in orbit around the Sun when it made 3 brief flybys of the planet in 1974-1975. In developing subsequent missions to Mercury, such as the U.S. Messenger spacecraft launched in 2004, spaceflight engineers calculated complex routes, making use of gravity assists from repeated flybys of Venus and Mercury over the course of several years. In the Messenger mission design, after conducting observations from moderate distances during planetary flybys in 2008 and 2009, the spacecraft entered into an elongated orbit around Mercury for close-up investigations in 2011. In addition, the extreme heat, not only from the Sun but also re-radiated from Mercury itself, challenged spacecraft designers to keep instruments cool enough to operate. Regardless, as the saying, "travel broadens the mind," scientific knowledge about Mercury was greatly increased by Mercury flybys. For instance, a completely unexpected discovery made by Mariner 10 was that Mercury possessed a magnetic field. Planets theoretically generate magnetic fields only if they spin quickly and possess a molten core. But Mercury takes 59 days to rotate and is so small, just roughly 1/3 Earth's size, that its core should have cooled off long ago. An unusual interior could help to explain the differences in Mercury's magnetic field when compared to Earth. Observations from Messenger revealed that the planet's magnetic field is approximately 3 times stronger in its northern hemisphere than in its southern. Scientists suggest that Mercury's iron core may be turning from liquid to solid at the core's outer boundary rather than the inner. In the words of Christopher Russell, a professor at the University of California, Los Angeles, who co-authored that model, "It's like a snowstorm in which the snow formed at the top of the cloud and middle of the cloud and the bottom of the cloud too. Our study of Mercury's magnetic field indicates iron is snowing throughout this fluid that is powering Mercury's magnetic field." The discovery in 2007 by Earth-based radar observations that Mercury's core may still be molten could help explain its magnetism, though the solar wind may play a role in dampening the planet's magnetic field. Although Mercury's magnetic field is just 1% the strength of Earth's, it is very active. The magnetic field in the solar wind, the charged particles streaming off the Sun, periodically touches upon Mercury's field, creating powerful magnetic tornadoes that channel the fast, hot plasma of the solar wind down to the planet's surface. In addition, Mariner 10's spectral measurements showed that Mercury has an extremely tenuous atmosphere. And that's really surprising. Previously, scientists still believed that a planet as small and as hot as Mercury has no possibility of retaining a significant atmosphere, if it ever had one. To be sure, Mercury's surface pressure is less than 1/trillionth that of Earth. Nevertheless, The traces of atmospheric components that have been detected have provided clues about interesting planetary processes. Mariner 10 found small amounts of atomic helium and even smaller amounts of atomic hydrogen near Mercury's surface. These atoms are mostly derived from the solar wind, the flow of charged particles from the sun that expands outward through the solar system, and remain near Mercury's surface for very short times, perhaps only hours, before escaping the planet. Mariner also detected atomic oxygen, which, along with sodium, potassium, and calcium, discovered subsequently in telescopic observations, is probably derived from Mercury's surface soils or impacting meteoroids and ejected into the atmosphere either by the impacts or by bombardment of solar wind particles. The atmospheric gases tend to accumulate on Mercury's night side but are dissipated by the brilliant morning sunlight. Many atoms in Mercury's surface rocks and in its tenuous atmosphere become ionized when struck by energetic particles in the solar wind and in Mercury's magnetosphere. Unlike Mariner 10, the Messenger spacecraft had instruments that could measure ions. During Messenger's first flyby of Mercury in 2008, many ions were identified, including those of oxygen, sodium, magnesium, potassium, calcium, and sulfur. In addition, another instrument mapped Mercury's long comet-like tail, which is prominently visible in the spectral emission lines of sodium. Although the measured abundances of sodium and potassium are extremely low, from hundreds to a few tens of thousands of atoms per cubic centimeter near the surface, telescopic spectral instruments are very sensitive to these two elements, and astronomers can watch thicker patches of these gases move across Mercury's disk and through its neighborhood in space. Where these gases come from and go was primarily of theoretical rather than practical importance until the early 1990s. At that time, Earth-based radar made the remarkable discovery of patches of highly radar reflective materials at the poles. Messenger later observed that the patches were made of water ice. Despite Mercury's proximity to the sun, the water ice was able to survive by being covered in an insulating layer of dark organic material in permanently shadowed regions of deep near-polar craters. The idea that the planet nearest the sun might harbor significant deposits of water ice originally seemed bizarre. However, Mercury has accumulated water over its history, most likely from impacting comets and asteroids. Water ice on Mercury's broiling surface will immediately turn to vapor, and the individual water molecules will hop in random directions along ballistic trajectories. The odds are very poor that a water molecule will strike another atom in Mercury's atmosphere, although there is some chance that it will be dissociated by the bright sunlight. Calculations suggest that after many hops, perhaps 1 out of 10 water molecules eventually lands in a deep polar depression. Because Mercury's rotational axis is essentially perpendicular to the plane of its orbit, sunlight is always nearly horizontal at the poles. Under such conditions, the bottoms of deep depressions remain in permanent shadow and provide cold traps that hold water molecules for millions or billions of years. Gradually, a polar ice deposit builds up. The susceptibility of the ice to subliming away slowly is reduced because it is cloaked by an insulating debris layer, or regolith, about 10 to 20 centimeters thick, made of organic compounds that also arrived on Mercury in cometary and asteroidal impacts. Another significant feature, Mercury speeds around the Sun every 88 Earth days, traveling through space at nearly 180,000 kilometers per second, faster than any other planet. Its oval-shaped orbit is highly elliptical, taking Mercury as close as 47 million kilometers and as far as 70 million kilometers from the Sun. If one could stand on Mercury when it is nearest to the Sun, it would appear more than 3 times as large as it does when viewed from Earth. Oddly, due to Mercury's highly elliptical orbit and the 59 Earth days or so it takes to rotate on its axis, when on the scorching surface of the planet, the Sun appears to rise briefly, set, and rise again before it travels westward across the sky. At sunset, the Sun appears to set, rise again briefly, and then set again. In 2016, a rare transit of Mercury happened, where the planet crossed the face of the Sun as seen from Earth. Mercury's transit may have yielded secrets about its thin atmosphere, assisted in the hunt for worlds around other stars, and helped NASA hone some of its instruments. As Mercury takes just Earth days to orbit the Sun, and Earth takes 365 days, approximately 3 or 4 times a year, Mercury overtakes Earth during its trip around the Sun, and an optical illusion occurs. Mercury appears to move backward across the sky for about 3 weeks. It is during this time Mercury is said to be in retrograde. Astrologers consider Mercury in retrograde to be a time of misfortune and miscommunication, as the perceived backward motion interferes with the planet's rules. The next complication to the puzzle involving Mercury is that the large global scarps and wrinkles first spotted by Mariner 10 were also spotted by Messenger, along with much smaller version if the same structures. The scarps, first identified in 1974 and 1975, are hundreds of kilometers long and several kilometers tall, enormous cliffs towering over the landscape. The latest observations supplement those with scarps a few kilometers long and only tens of meters tall, and more importantly, geologically young. The larger scarps are ancient and softened by the passage of time, but the smaller ones are crisp and fresh, likely formed within the last tens of millions of years. This suggests that instead of being cold and dead, Mercury is still geologically active today as a hot core cools, the planet shrinks, and the surface crumples. But the story of Mercury gets stranger still. When mapping the geology of Mercury's surface, Messenger found distinct regions of unique geochemistry, a mix of terrains instead of a single, roughly similar surface. The spacecraft also spotted delicate volatiles like potassium and uranium, chemicals that should have been destroyed by the enormous heat of a crust-shearing collision or the scorching heat of a crust-boiling sun. By their very presence, these chemicals argued against either theory for Mercury's oddly large core, leaving scientists scrambling for a new theory. More data poured in from Messenger, with scientists identifying pyroclastic flows that could only be the result of explosive volcanism of lava mixed with volatile gases like water and carbon dioxide. More chemicals scientists didn't expect in abundance on a planet so near the Sun. Soon after, the spacecraft's radar spotted water ice lurking in the shadows of polar craters, reminiscent to the ice hiding in polar craters of our Moon. The Messenger mission came to an end in 2015, the spacecraft running out of fuel and deliberately crashing into the planet. Now scientists are left analyzing and reanalyzing the data from its 4005 orbits to try to piece together a new explanation for how Mercury formed that pull all these pieces together. But in all the mysteries lays a tantalizing new possibility for investigating this deceptively simple planet: quakes. If Mercury truly does have a hot, liquid core and is geologically active today, every time the crust moves to create a new ridge or wrinkle, a quake releases seismic waves propagating through the planet. On Earth, we detect that seismic energy with seismometers, observing the speed and distribution of the waves to map the planet's interior. Astronauts did the same thing on a smaller scale during the Apollo missions, observing moonquakes to understand what was going on below the surface. Scientists are planning to apply the same trick on Mars, sending a seismometer on NASA's delayed InSight lander to peer into the interior or Mars. This same idea could work on Mercury, with observations of seismic waves pinning down the true size and structure of the core, and detecting if, like the Earth, it has a warm liquid outer core around a solid interior. And if we can do that, we'll be one step closer to understanding how Mercury formed, why it is the way it is today, and what to expect of other rocky planets around distant stars. Another long-awaited mission is Bepi Colombo, a joint mission of the European Space Agency and the Japan Space Exploration Agency. It will be only the second and the most complex mission in history to orbit Mercury. Its two orbiters, the European Mercury Planetary Orbiter and the Japanese Mercury Magnetospheric Orbiter, carry a combined 16 scientific instruments that will help shed light on some perplexing questions. Do the scorched planet's polar craters really harbor water ice? Where does Mercury's magnetic field come from? What are the strange hollows on its surface? The mission, launched on October 19, 2018, is expected to reach Mercury in 2025, after a complicated 7-year journey, which requires 9 flyby maneuvers, including 1 at Earth, 2 at Venus, and 6 at Mercury itself. These flybys slow down the spacecraft against the gravitational pull of the Sun so that it can safely enter the orbit around the innermost planet of the solar system. During the epic journey, the 2 orbiters travel stacked on top of an ESA-built Mercury transfer module. The module, with its 15-meter solar arrays, supplies power during the interplanetary cruise. It is also fitted with 3 selfie cameras, originally used to monitor the deployment of the solar arrays and antennas after launch. But these cameras are regularly being used by the Bepi Colombo team to obtain simple black and white images of the spacecraft's whereabouts. Thanks to these cameras, Bepi Colombo is sending regular postcards home from its encounters with various planets during the flybys. In April 2020, the spacecraft waved goodbye to Earth during a flyby at a distance of 12,700 kilometers. In October 2020 and August 2021, Bepi Colombo flew past Venus. The first flyby saw the spacecraft zip by at a distance of 10,620 kilometers from Venus. However, the second took it incredibly close, only 550 kilometers above the hot, cloudy planet's surface. This enabled scientists to take some unique measurements of Venus's murky atmosphere. Once the stacked spacecraft reaches its destination, the MTM will separate from the orbiters. Then, the 2 spacecraft will each be put in separate orbits to perform scientific investigations of Mercury. Japan's MMO will have an orbit of 9.3 hours, and Europe's MPO an orbit of about 2.3 hours. The mission is expected to last for 1 Earth year, an equivalent of 4 Mercury years. It may be extended for an additional Earth year if funding allows, and the 2 spacecraft remain in good health. Elsewhere, scientists also expect our most powerful space observation to take some photos of Mercury. James Webb is made up of a 6.5-meter, gold-plated mirror, a sunshield that is the size of a tennis court, and an array of complex instruments that are cooled to temperatures only a few degrees above absolute zero. These features allow the telescope to observe the heavens in infrared radiation, revealing details of the universe just after its Big Bang birth 13.8 billion years ago, and images of stars being born in dust clouds. However, the telescope is providing science with a further gift. For infrared radiation also turns out to be ideal for studying extrasolar planets, or exoplanets, as worlds that orbit other stars are known. But how can Webb analyze exoplanets' atmospheres? We all know that measuring a planet's atmosphere from hundreds or thousands of light years away is not as daunting as it may sound, though it certainly requires specialized instruments and rigorous techniques. One method is known as transmission spectroscopy. Here's how it works. Webb will first observe the star itself to obtain its spectrum. Next, Webb will wait until the exoplanet passes in front of its star and then measure another spectrum. At this point, the exoplanet will be backlit, which means the light of the star filters through the planet's atmosphere toward Webb. The planet's atmosphere will absorb some of that starlight, which will appear as dips in the spectrum. When researchers subtract the spectrum of the star from the combined spectrum of the star and the exoplanet, they are able to isolate which light was absorbed when it passed through the exoplanet's atmosphere. Next, they will compare the light absorption dips with extensive references that detail the light absorption of every molecule we've witnessed on Earth to determine which molecules are present in the exoplanet's atmosphere. An early target for astronomers using the James. Webb has been TRAPPIST-1, a small, cool star of a type known as a red dwarf. 40 light-years from Earth, it has a family of 7 small rocky worlds, 3 of them lying within a region known as the habitable zone. Here, conditions are not too hot and not too cold to prevent water from existing as a liquid, a prime requirement for life to flourish, say astrobiologists. However, analyses using the James Webb of two of the star's innermost planets, TRAPPIST-1b and TRAPPIST-1c, have revealed they possess either no atmosphere or only a very thin one. Further Webb studies of the rest of the system are now being planned. TRAPPIST-1's system still looks promising if you are seeking a world that might support life, said astronomer Dr. Joe Barstow of the Open University. However, one special problem does affect studies of stars like TRAPPIST-1. Red dwarfs are spotty. This may not sound like a terminal condition, but it does have serious implications. As Barstow said, our own sun has sunspots that are associated with intense solar activity, but it has relatively few. By contrast, TRAPPIST-1 has dozens of spots that change all the time, and that makes it very difficult to differentiate between these and features of a planet's atmosphere. The TRAPPIST-1 system is not going to give up its secrets easily. Ultimately, astronomers using the Webb telescope to seek out signs of extraterrestrial life are looking for a set of biological markers known as the Big Four: oxygen, carbon dioxide, water, and methane. Their presence in the atmosphere of an exoplanet would be a strong sign that life of some kind exists there. The life of the James Webb Space Telescope promises to be an intriguing one and lengthy. James Webb's flight on an Ariane 5 rocket from the European Space Agency's launch pad in Kourou in French Guiana to its current position in orbit round the Sun was near flawless. The observatory used very little fuel to maneuver itself into its exact target location, and that means there will be extra to allow the telescope to orient itself for far longer than anticipated. Space engineers have calculated Webb's expected 10-year lifetime could be doubled. In many ways, that is very good news. We will be able to do a lot more science with it now. We are going to learn so much about the chemistry of their atmospheres and are going to find some very strange and bizarre worlds out there. It is tremendously exciting. And if one day astronomers announce they've found an Earth analog among the stars, what's next? The implicit part of the question is whether we can travel to it and live there. But simply put, we can't. It's not like we can go there. There's no USS Enterprise we can use to warp over to the nearest Earth 2.0, and without faster-than-light travel, it would be a long trip. Even the fastest spaceship ever launched would take the better part of a millennium to get to the nearest star system, Proxima Centauri, which does actually host an Earth-sized planet that might be within our range of acceptability. Better pack a lunch. So many sci-fi movies tell us we need to evacuate Earth that it's a trope. This idea is far more fi than sci, though. Humanity increases its number by more than 70 million people every year. You'd need to launch 2,000 SpaceX starships every day just to keep up with that increase, even ignoring the less than helpful travel times. Easing population pressure via interstellar immigration is a non-starter. Establishing a settlement is a tall order, too. We don't even really know how to do this in low Earth orbit, on the Moon or on Mars. We're a long, long way from being able to set up shop on an alien Earth, even if we could easily get to one. Regardless, what's important is that it may also help us answer the most fundamental question humans have ever had. How did we get here? For millennia, this question has inspired speculation, myth, religion, and philosophy. With a distant blue-white world hovering in the eyepiece, it becomes science. So, scientifically speaking, we look for other planets because we want to understand how they form, how conditions change their physical properties, and how they differ from or mirror the planets in our own solar system. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.
Okay, retro, go. Vital, go. Guide, go. Control, go. Telcom, go. GNC, go. Econ.
While the moon has always been an object of wonder and scientific interest to humanity, lunar exploration began in earnest in the 1950s, with the United States and the USSR developing and launching robotic spacecraft. In 1959, the USSR's Luna 1 was the first spacecraft to fly by the moon. In 1966, Luna 9 achieved the first soft landing, and in 1969, the US's Apollo 11 achieved the first human landing. In the decades since, many nations have contributed to lunar orbiters and landers. As of January 2024, 5 nations have successfully landed on the moon. But despite the incredible achievements, there was one aspect of the moon that remained out of reach: the far side. The far side of the moon has a certain mystique about it. It's eternally out of view, never facing the Earth, which has earned it a misleading nickname, the dark side, as if sunlight never reaches its surface. It's the section of the moon we'll never see for ourselves, not unless we hop on a spaceship and fly over there. But now, thanks to the James Webb Space Telescope, we can finally see what lies beyond the horizon, unlocking a new era of lunar exploration and discovery. Join us as we explore the mysterious realm of the moon's dark side, uncovering obscure details and highlighting our celestial neighbor's lesser-known features. Some people see a face in the moon, others see a rabbit or a toad. But regardless of what you see on the lunar surface, we all view the same side of our natural satellite. So, why don't we ever see the far side of the moon? To know why, let's look more closely at its relationship to Earth. The moon orbits in such a way that one rotation takes just about the same length of time as it takes for it to orbit around Earth. That is, the moon spins on its own axis once during its orbit around our planet. That leaves one side facing us during its orbit. The technical name for this spin-orbit lock is tidal locking. Of course, there is literally a dark side of the moon, but it's not always the same side. What is darkened depends on which phase of the moon we see. During a new moon, the moon lies between Earth and the sun. So the side we normally see from here on Earth that's normally lit by the sun is in its shadow. Only when the moon is opposite from the sun do we see that part of the surface lit up. At that point, the far side is shadowed and is truly dark. The far side of the moon was once mysterious and hidden. But that all changed when our first glimpse of the mysterious far side came early in the space race, courtesy of the Soviet Union's Luna 3 spacecraft almost 60 years ago. In 1959, barely 2 years after placing Sputnik 1 in orbit, Russian engineers managed to send the spacecraft, which was crude by today's standards, into orbit around the moon, and for the first time, we got a good look at the mysterious far side. Luna 3 took 29 film images of the far side in total, which were photographically developed, fixed, and dried on board. Remember, this was long before multi-megapixel cameras. Ironically, the film used had been stolen from American spy balloons, as it had to be sturdy and radiation-hardened. The spacecraft, using a combination of 2 camera systems, one wide field and one narrow field but higher resolution, and a crude onboard scanner, could then transmit the processed images, which were spot-scanned from the photographs, back to the receiving station in the former Soviet Union. Although only 17 of the 29 taken were transmitted successfully back to Earth, of which 6 were considered good enough for publication, they proved to be a revelation. Those 6 images covered 70% of the far side and opened a whole new perspective on the lunar surface. It was almost immediately evident that the dark patches that make the face of the man in the moon on the near side are almost completely absent on the far side. These dark patches are basaltic plains called mare, created by volcanic activity on the moon billions of years ago. Instead, the far side was littered with craters, even more so than the near side, and some of those craters were the size of small countries. The Soviets started naming many of the features they were seeing for the first time, an act which caused some controversy in what was known as the height of the Cold War era. We already had an inkling of one of those vast new craters, which is actually one of the very few mare on the far side. The subtlest hint of Mare Orientale, one of the largest impact craters known, seen on the limb of the moon, had been known of since its discovery by Julius Franz in 1906, and can be seen during good librations when that portion of the moon swings around towards us. The view from Luna 3 showed how vast an impact crater Orientale was, resembling a bullseye. It was almost 900 kilometers across, pretty much the length of the United Kingdom, give or take, and was caused by an asteroid impact, thought to be around 64-kilometer wide just under 4 billion years ago. The resulting giant crater, termed an impact basin, was subsequently filled with volcanic lava. In 1965, another Soviet mission, Zond 3, flew by the moon with a far better camera than Luna 3 possessed, and with the ability to conduct more detailed science observations, including spectroscopy. Zond 3 produced 23 very detailed photographs of the lunar far side, which enabled one of the first detailed maps of the entire lunar surface to be constructed. In the meantime, NASA was progressing its Apollo program at a phenomenal rate. Following the declaration by President Kennedy that the U.S. would place a man on the moon and return him safely to the Earth by the end of the 1960s, by December 1968, NASA was ready to send 3 people, including Frank Borman, Jim Lovell, and Bill Anders, all the way around the moon and back for the Apollo 8 mission. They became the first humans in history not only to escape from low Earth orbit, but also to see the elusive far side. This is how Lovell famously described the lunar surface. The moon is essentially gray, no color, looks like plaster of Paris or sort of a grayish beach sand. We can see quite a bit of detail. There's not as much contrast between that and the surrounding craters. The craters are all rounded off. There's quite a few of them. Some of them are newer. Many of them look like, especially the round ones, look like they were hit by meteorites or projectiles of some sort. When the Apollo 8 spacecraft flew around the far side of the moon, the signal to Earth was cut off for around 10 minutes. This loss of signal was a daunting time for the flight crew and mission control. Apollo 8 was alone and truly cut off from Earth, venturing where no human had ever gone before. As the astronauts came back around from the far side, a collective sigh of relief was breathed by many of the flight team at Mission Control in Houston. Charlie Duke, who was the lunar module pilot on the Apollo 16 mission, describes what it was like to be flying over the far side of the moon. In the words of Charlie, "The computer told us that we were out of contact with the Earth and that we had loss of signal. Then, all of a sudden, there was the sunrise. It was the most dramatic sunrise I've ever seen. In Earth orbit, you see the sun's glow on the horizon or the planet's atmosphere, and it gets brighter and brighter. The moon is different, though. There's instant sunlight with long shadows on the lunar surface. The far side of the moon was very rough back there. I would not have wanted to land on the backside of the moon." After the success of Apollo 8, Apollo 9 went back to vital low Earth orbital testing of the lunar module. So the next astronauts to visit the far side were Gene Cernan, John Young, and Tom Stafford, on board Apollo 10 in May 1969, just 2 months before the historic landing of Apollo 11. However, while flying over the far side of the moon, the trio of astronauts encountered something strange, which in the last few years NASA has been forced to re-explain thanks to conspiracy theory documentaries airing on US television. The facts had been well known since the 1970s. These strange events on Apollo 10 were manifest in the form of some very odd sounds. The radio systems on board the Apollo spacecraft were crude by modern standards, though state-of-the-art at the time. The command and lunar modules were relatively noisy environments, according to most of the astronauts, with bumps and bangs combined with the whirring of fans and engine noise. What the Apollo 10 crew heard through the radio systems baffled them. They described it as being almost like that made by an electronic instrument called a theremin, often used in creepy science fiction B-movies of the 1950s and 60s, as well as on the Beach Boys song Good Vibrations. Research has since proven that the sound was nothing more than an interference effect from those 1960s radio communications systems on board. With the onset of the moon landings, 2 astronauts would travel to the surface, while a third remained on board the command module to orbit the moon alone, though all of them got chance to orbit the moon and see the far side before landing. The solo orbital journeys of Michael Collins, Apollo 11, Dick Gordon, Apollo 12, Stuart Roosa, Apollo 14, Al Worden, Apollo 15, Ken Mattingly, Apollo 16, and Ron Evans, Apollo 17, who were the unsung heroes of the Apollo missions, are some of the bravest feats ever achieved by astronauts. They would spend days making quite detailed lunar observations from orbit, mapping features nobody had ever seen before. Al Worden is often quoted as saying that his time alone was some of the best he had during the Apollo 15 mission. According to Al Worden, the far side, the views at certain times when the sun and the earth are blocked out, are like nothing you could imagine. The sheer number of stars you see is incredible. It's like a sheet of white, and you know that every single one of them is a sun in its own right. A question often asked of the Apollo astronauts and flight teams is, why were all the missions just to the near side? In fact, the answer is so simple. As Charlie Duke says, we wanted to be in contact with the Earth, so we weren't able to land on the far side of the moon. Should something have gone wrong while the astronauts were on the surface, they would not have been able to communicate directly with Earth. This would not be such a problem today, as satellites could be put into lunar orbit to relay communications. The far side is of growing interest to scientists and potentially future planned human missions. Indeed, the possibilities for the far side of the moon are vast. For many decades, the astronomical and scientific community has wanted to put radio telescopes and optical telescopes on the far side. Observatories on the far side would be shielded from not only man-made radio interference from Earth, but also the glare of daylight on our planet. The telescopes could be built inside craters to avoid solar radiation, and would provide us with an unprecedentedly clear insight deep into the far reaches of the universe. Otherwise, we also have little true understanding of the processes that make the far side so vastly different in appearance to the near side. Thus, with NASA gearing up to send astronauts to the moon's south pole, there's never been a better time to be a lunatic. The surge of interest in lunar exploration is great news for planetary scientists, hoping to learn more about Earth's rocky sidekick. These are the burning questions they're dying to find the answers to. According to Noah Petro, a research scientist at NASA's Goddard Space Flight Center in Greenbelt, Maryland, and a project scientist for the Lunar Reconnaissance Orbiter, the fundamental question of how the moon formed and how that relates to the Earth is really the most important of the unknowns. Everything else comes after that. You can thank Apollo 11 for giving us our first insight into that mystery. The mission brought back 50 pounds worth of moon rocks and initiated decades of investigations focused on learning how the moon formed and evolved. Scientists used them to come up with the strongest existing model, that the moon began as a magma ocean, a giant ball of molten lava orbiting Earth. This in turn led decades later to the hypothesis that the moon was born out of Earth itself, when a giant impact with a Mars-sized object ejected debris into orbit. Further studies of the rock show the material that formed the moon also formed our own planet, adding more support to this idea. That's the most widely accepted hypothesis for the origin of the moon, but it's by no means perfect. There is no way yet to confirm a giant impact created the moon, and our sense of how the magma ocean cooled down into the dry, gray rock we see now is still very hazy. About 10 years ago, we discovered evidence of water on the moon, something that's a bit difficult to reconcile with an impact hypothesis. Getting to the bottom of the moon's past requires the sort of on-the-ground work we've done to unravel Earth's own history. Put the origin of the moon aside, Apollo moon rocks continues to challenge our understanding with another conundrum. Why aren't moon rocks as old as the moon? The moon is just over 4.5 billion years old, which makes it a mere 60 million years younger than the solar system itself. The early days of the inner solar system were chaotic and defined by the constant collision of solid materials as they whipped around the nascent sun, gradually forming larger and larger bodies in a process known as planetary accretion. Analysis of the rocks collected by the Apollo astronauts shows that most were created by impact events about 3.9 billion years ago, but almost none of them were dated to the moon's first 600 million years of existence. This is weird because impact events should have become less frequent as the planetary accretion process wound down, so you'd expect to find a lot more rocks formed from earlier collisions. This led scientists to hypothesize that the moon was subject to intense collisions about 3.9 billion years ago, a period known as the Late Heavy Bombardment, or more poetically, the Lunar Cataclysm. While this theory nicely accounts for the Apollo moon rocks, it also raises a big question. What caused all these rocks to start pummeling the moon? The leading model suggests that the outer planets used to orbit much closer to the sun, and as they moved outward, sent big rocks on a collision course with the moon. But an alternative theory posits that the cataclysm never happened and that the preponderance of rocks dating to 3.9 billion years ago is due to sample bias. The last 3 Apollo missions all took samples from 3 major impact craters: Imbrium, Serenitatis, and Nectaris. New evidence suggests that the samples used to date the age of each of these craters, which is crucial to determining whether a period of heavy bombardment occurred, may actually just be debris from the impact that formed the largest crater, Imbrium, about 3.9 billion years ago. So, the best way to settle the lunar cataclysm debate will be to visit craters where samples aren't likely to have been contaminated by the Imbrium impact, such as the South Pole or the far side of the moon. If most of those new samples are older than 3.9 billion years, it will cast the theory of the lunar cataclysm in serious doubt and also help scientists better understand conditions in the early solar system. Regardless, interest in the lunar South Pole as a landing site is mainly driven by the fact that scientists know the region hosts lunar water. Indeed, there's water on the moon, and NASA first found water on the moon in 2009. But we're not just talking about a little sprinkling of interstellar water. We're talking about troves and troves of water ice that could be sitting just beneath the surface, especially at the lunar poles. This is good news for future expeditions to the moon, which plan to use this water ice for everything from life support to rocket fuel. But for many scientists, the big question is, how did all that water ice get there? Well, nobody really knows yet. According to Paul Hayne, a planetary scientist at the University of Colorado Boulder, there are 3 main theories for how water originated on the moon. The most obvious theory suggests that the water ice was deposited by asteroid and comet impacts, where it vaporized and eventually made its way to the poles. It's also possible that ionized hydrogen from solar winds binds with oxygen trapped in regolith and is eventually released as vaporized water due to temperature fluctuations on the surface. Finally, there's a possibility that water was present in the material that originally formed the moon and was forced to the surface by volcanic eruptions. It could be that all 3 processes were at work, which makes it a question of how much water each mechanism contributed. Luckily, there has been some promising initial data. In 2009, NASA launched the Lunar Crater Observation and Sensing Satellite on a mission to impact the lunar surface at the South Pole. And this mission not only detected the presence of water, but it also identified a mix of other materials that are common in comets, suggesting at least some of the water hitched a ride on space rocks. To get a better idea of how much of the moon's water was brought to the lunar surface by comets, asteroids, or solar winds, it will be necessary to send a robot or human to take a sample and examine its isotopic composition. That's really the only way we can definitively associate that material with a source. But even if scientists can determine the origins of lunar water, there's still the question of how it came to be concentrated in the poles, a controversial topic, according to Hain. Currently, the lunar science community is divided on whether water that is vaporized during comet and asteroid impacts can travel across the surface of the moon or whether it becomes trapped in the regolith. The only way to know for sure is to return for further tests. One of the biggest questions facing lunar scientists is whether the moon houses alien life. Conspiracies about little green men aside, some scientists believe water stored under the satellite's surface may hold ancient microbes. According to Professor Christopher Palma, an astrophysicist at Penn State, one idea for the origin of life is that its building blocks were delivered by comets. There may be remnants of those in the ice on the moon. Scientists won't know for sure until they send a probe, or human, up to the lunar surface armed with a hefty drill. One enigma that's sprung up only recently has to do with the discovery that something massive is lurking underneath the south pole of the moon, below the largest impact crater ever made in the entire solar system. Scientists have no idea what it could be, but it's certainly big enough to affect the gravitational force exerted by the moon's mass. Predominant theories suggest it's some sort of heavy metal body from a projectile that impacted the surface a long time ago. But this is far from certain. And it's hard to understand what this mass is doing suspended underground. We know the moon's interior is still active to some degree, and heat should have caused this mass to shift around instead of staying trapped like Han Solo in carbonite. Put simply, the moon, once again, raises questions we're just not able to answer yet. Another stunning revelation showed there are earthquakes happening on the moon pretty frequently, otherwise known as moonquakes. Apollo-era seismometers installed on the surface measured these shakes from 1969 to 1977. That data has shown us that the moon is an active body, a far cry from the stale, lifeless rock many assume it is. We're already aware of a few phenomena that cause these quakes, like thermal expansion, tidal stress induced by Earth's gravity, and meteorite impacts. But with such limited data, we're not entirely sure how these processes work and exactly how the quakes behave. Moreover, there are other, shallower moonquakes without any obvious cause, which seem to be occurring more recently than the others. Petro suggests a global seismic network installed around the moon would be tremendously helpful in helping understand the trigger mechanisms behind all this tectonic activity. Such a network could cleanly identify exactly when these events occurred, where they originated from, and the effect they have on the rest of the moon. The 50-year-old data we're using now won't be enough to give us any good answers. In addition, scientists also believe that there's a reason we've only ever seen one side of the moon. It's tidally locked, which means only one side of it faces Earth. This is not uncommon for moons in our solar system, but it's still unclear exactly when this occurs, what conditions encourage it, and how it happens. So, in some scientists' mind, this mystery of tidal locking harkens back to the question of the origin of the moon and what was happening in early lunar history. It's another piece of the 4-billion-year puzzle. What's more, this mystery isn't just local to the moon either. As we continue to find more planets and moons outside of our solar system, it's important to figure out what sort of factors help incite features like tidal locking and decide whether potentially habitable worlds, like the TRAPPIST-1 exoplanets, really are hospitable to life. After all, if scientists can lift the veil on moon mysteries, we could have a better understanding of the solar system's history. The moon lacks much in the way of an atmosphere and hasn't been volcanically active for billions of years, which means its surface has remained relatively unchanged across the eons. In this sense, says Prabal Saxena, a postdoctoral researcher at NASA's Goddard Flight Center, the craters are like the pages of a history book of the early solar system, if only we could figure out how to read them. As mentioned previously, a prevalent theory of lunar formation says that our planetary neighbor was bombarded by space rocks about 3.9 billion years ago. If the samples from the surface confirm that there was a lunar cataclysm, this could also tell us a great deal about how the solar system formed. Not only would it suggest that the outer planets were once much closer to the Sun, it would likely mean that the Earth was bombarded too. This would have vaporized any water on the Earth's surface and killed any life that may have existed there. Strangely enough, the Moon also appears to have recorded early solar history. Just a few years ago, Saxena and his colleagues used the composition of the lunar crust to determine that our Sun likely rotated 50% slower than similar newborn stars during its first billion years of life. The Moon and Earth are largely composed of similar materials, but the Moon has notably less sodium and potassium. Using this evidence, Saxena and his colleagues ran simulations that showed how solar activity can either deposit or strip the Moon of these minerals, and then incorporated data about the relationship between solar flares and stellar rotation rates. According to the simulations, the Sun must have been rotating slowly to account for the levels of potassium and sodium observed on the Moon today. This data about the Sun's early history can also help explain things like how quickly Venus lost its water, how quickly Mars lost its atmosphere, and how it impacted atmospheric chemistry on Earth. As NASA and other space agencies lay the foundations for a permanent human presence on the Moon, there will be more big questions to answer, and the Moon is really just a small step toward the giant leap of unraveling the origin of everything we know. The James Webb Space Telescope is a revolutionary instrument destined to unveil the deepest mysteries of the cosmos. With its unparalleled ability to peer into the distant reaches of the universe, the premier telescope was expected to bring clarity to several long-standing questions in cosmology. However, as the data started rolling in, instead of resolving these questions, Webb's discoveries have paradoxically deepened the crisis in cosmology, challenging our most cherished models and theories about the universe. But to better understand the world-shattering revelations of James Webb, the first thing to do is take a quick look at the Standard Model of Cosmology and its problems. The Standard Model of Cosmology, also known as the Lambda Cold Dark Matter, or LCDM model, has been remarkably successful in explaining a wide range of observations about the universe, from the CMB for cosmic microwave background radiation to the large-scale structure of the cosmos. However, despite its successes, the LCDM model is not without its problems. One of the most significant components of this model is dark matter, which is believed to make up about 27% of the universe's total mass energy content. Dark matter is essential for explaining the formation of galaxies and the observed rotation curves of galaxies, which cannot be accounted for by visible matter alone. However, despite extensive efforts, dark matter has never been directly detected. Thus, the exact nature of dark matter remains one of the biggest mysteries in cosmology. Various candidates have been proposed, ranging from weakly interacting massive particles, also known as WIMPs, to axions and sterile neutrinos, but none have been conclusively observed. This lack of direct detection raises questions about the very existence of dark matter as a physical entity. Some physicists have even suggested that our understanding of gravity might need to be modified, a hypothesis known as MOND, though this idea is not widely accepted in the cosmological community. Another major component of the LCDM model is dark energy, which is thought to make up about 68% of the universe's mass energy content, and is responsible for the observed accelerated expansion of the universe. Dark energy is often modeled as a cosmological constant, which Einstein originally introduced to his equations of general relativity. However, similar to dark matter, the nature of dark energy remains entirely unknown. The cosmological constant problem is one of the most significant theoretical issues in modern physics. The observed value of the cosmological constant is many orders of magnitude smaller than what quantum field theory predicts, leading to a profound mismatch between theory and observation. This discrepancy suggests that our understanding of the underlying physics is incomplete. Some have proposed alternative models, such as quintessence, where dark energy is dynamic rather than constant, but these models also face significant challenges. While the dark universe remains elusive, the rate at which the universe is expanding is even more mysterious. The notion of an expanding universe first emerged in the 1920s, largely due to the work of Edwin Hubble. Hubble's observations of distant galaxies revealed that they were moving away from us, with their velocities increasing proportionally to their distance. This observation led to the formulation of Hubble's law, which states that the velocity at which a galaxy recedes from an observer is directly proportional to its distance from the observer. The constant of proportionality became known as the Hubble constant. Hubble's discovery was groundbreaking, fundamentally altering our understanding of the universe. It suggested that the universe was not eternal and unchanging, but dynamic, with galaxies moving apart as space itself expanded. This revelation was key in the development of the Big Bang theory, which posits that the universe began as an incredibly hot and dense point and has been expanding ever since. The crisis surrounding the expansion rate of the universe arises from the fact that different methods of measuring the Hubble constant yield different results. These discrepancies are not trivial. They point to potential gaps in our understanding of the universe's fundamental properties. There are two primary methods used to measure the Hubble constant: the early universe method and the late universe method. The early universe method involves analyzing the cosmic microwave background radiation, the afterglow of the Big Bang, using data primarily from the Planck satellite. This method gives a value of the Hubble constant around 67.4 kilometers per second per megaparsec. On the other hand, the late universe method involves observing distant galaxies and supernovae, using a cosmic distance ladder to measure their distances and velocities. The most precise measurements using this method, particularly from the SHEUS team, led by Nobel laureate in physics Adam Rees, yield a value around 73.4 kilometers per second per megaparsec. The problem is clear. These two measurements of the Hubble constant do not agree, and the discrepancy is significant, on the order of 5%, which is far beyond the margin of error for these types of measurements. This tension has led to what is now commonly referred to as the Hubble tension, a term that encapsulates the crisis in cosmology. The Hubble tension is not just a technical problem or a matter of fine-tuning measurements. It has deep implications for our understanding of the universe. If the discrepancy is real and not due to some unaccounted-for systematic error in the measurements, it suggests that our current cosmological model, the lambda cold-dark matter model, might be incomplete or even incorrect. The LCDM model is the standard model of cosmology. It describes the universe as being composed of three major components: ordinary matter, the stuff that makes up stars, planets, and us; dark matter, a mysterious form of matter that does not emit, absorb, or reflect light, but exerts gravitational effects; and dark energy, a form of energy that permeates all of space and is responsible for the accelerated expansion of the universe. The early universe measurement of the Hubble constant is deeply rooted in the LCDM model. If the late universe measurements, which are independent of the early universe methods, continue to show a different value for the Hubble constant, it may indicate that something is missing in our current understanding of dark energy, dark matter, or some other aspect of the cosmos. This could potentially lead to new physics beyond the standard model, which currently describes the fundamental particles and forces in the universe. Several theories have been proposed to explain the Hubble tension. One possibility is that there could be a problem with the data or the methods used in the measurements. However, the teams involved have rigorously checked their data and methods, and no significant errors have been found that could account for the discrepancy. Another possibility is that new physics is at play. For example, some theories suggest the existence of a new form of dark energy that varies over time or space, unlike the cosmological constant used in the LCDM model. This could alter the expansion rate of the universe at different times, leading to different values for the Hubble constant, depending on the method used. Other theories propose that there could be a previously unknown interaction between dark matter and dark energy, or that there could be an additional type of neutrino, often referred to as a sterile neutrino, which could impact the expansion rate. There are also suggestions that the geometry of the universe might not be as simple as currently thought, with some models proposing a non-flat or even a cyclic universe. In short, while the standard model of cosmology has provided an incredibly successful framework for understanding the universe's history and structure, the issues outlined ranging from the unresolved nature of dark matter and dark energy to the cosmological constant problem, the Hubble tension highlights significant gaps in our current knowledge. These problems suggest that while the LCDM model is an excellent approximation, it may not be the final word on cosmology. New observations, theories, and experiments in the coming years may lead to a deeper understanding of these issues, potentially revealing new physics and reshaping our view of the universe. The quest to resolve these problems is not only crucial for cosmology, but also for our broader understanding of fundamental physics. That's why, when the James Webb Space Telescope began its mission, it was expected to provide more precise measurements that could potentially resolve the Hubble tension and offer new insights into dark matter and dark energy. However, Webb's findings have, in many ways, deepened the crisis rather than alleviating it. The latest results form James Webb put the average value of the Hubble constant, key in determining the rate at which the universe is expanding, at 69.96 kilometers per second per megaparsec. This is indeed consistent with predictions stemming from the standard model of cosmology, which should sound like an end to the issue. But the findings also highlight a critical disagreement. In other words, new discoveries from James Webb is adding to the confusing drama of Hubble tension. This is the conclusion made by a research team led by University of Chicago astronomer Wendy Friedman. Friedman's team, working on a project called the Chicago Carnegie Hubble Program, or CCHP, used the Webb telescope to measure the distance to 10 relatively nearby galaxies that have all been observed to have had a type Ia supernova occurrence. The distance measurements were then cross-checked by 3 independent means. The first of these 3 independent methods is known as the tip of the red giant branch, which describes the maximum brightness that evolved sun-like stars called red giants can reach. The second method involves something called the J-region asymptotic giant branch, which refers to a flavor of red giant stars that are rich in carbon and that have similar intrinsic infrared brightnesses. The third cross-check was done with Cepheid variable stars, which have a period luminosity relation first discovered by Henrietta Swan Leavitt in 1908, which connects the period of pulsation with maximum luminosity. In other words, simply by measuring how long a star takes to pulse, we can calculate what its maximum brightness should be and compare that to how bright it appears in the night sky to deduce how far away it must be. The CCHP team measured the Hubble constant as 69.85 kilometers per second per megaparsec using the tip of the red giant branch, and they measured 67.96 kilometers per second per megaparsec using the carbon stars. So far, so good. The associated error bars encompass the Planck measurement of the Hubble constant, putting them in good agreement with the standard model. However, the Cepheid variables, though, were not playing ball. From them, the CCHP team arrived at a value of 72.04 kilometers per second per megaparsec, which is not in agreement with the other measurements. Taken together, the four methods give an average value of 69.96 kilometers per second per megaparsec. To the contrary, it looks like our standard cosmological model for explaining the evolution of the universe is holding up. But the Cepheid variable measurements do seem to continue to provide tension. Cepheids form the bottom rung of the cosmic distance ladder, with type Ia supernovas as the next rung up because they can be seen out to greater distance than Cepheids. In the work by Adam Rees's SHIRUES group, Cepheids are crucial for calibrating the type 1a supernova measurements. However, Friedman has in the past expressed concerns about a potential problem called crowding. Although the Hubble Space Telescope has sufficiently powerful resolution to identify Cepheid variable stars in other galaxies, it is possible that low-mass stars very close to a Cepheid can be unresolved and end up blurring in with the light from the Cepheid, thus affecting scientific results. Earlier this year, Rees led a team that used the James Webb Telescope to double-check Hubble's observations of Cepheids and came to the conclusion that crowding was not an issue. However, in their research paper, Friedman and fellow researchers point out that the two methods least affected by crowding, the tip of the red giant branch and the carbon stars, give values in accordance with the standard model. While attention will now focus on measurements of galactic distances using Cepheid variables, more measurements with the James Webb of galaxies with type Ia supernovae will be invaluable for confirming the results from these 10 galaxies. However, type 1a supernovas in galaxies that also have resolvable Cepheids, red giants and carbon stars, are relatively rare, meaning it may take some time to get a large enough sample. Regardless, it's really worth waiting. And while James Webb deepened the crisis in cosmology, challenging many of the assumptions and theories that have guided our understanding of the universe for decades, it is transforming our understanding of the universe in ways that were previously unimaginable. Its ability to observe the universe in the infrared spectrum has opened up new windows into the early universe, the formation of galaxies, the birth and life cycle of stars, the properties of exoplanets, and the nature of dark matter and dark energy. In just a short time since its launch, the Supreme Observatory has already made groundbreaking discoveries that are challenging our current models and expanding the frontiers of knowledge in astrophysics and cosmology. One of the primary objectives of the James Webb Space Telescope is to study the early universe, particularly the formation of the first galaxies. The telescope's ability to observe in the infrared allows it to see light from objects that are billions of years old. Light that has been stretched into the infrared spectrum due to the expansion of the universe. This capability enables the Webb telescope to observe the universe as it was only a few hundred million years after the Big Bang, a time period that has been largely inaccessible to previous telescopes. Before James Webb's debut, our understanding of the early universe was based primarily on theoretical models and indirect observations. The Hubble Space Telescope provided some glimpses of distant galaxies, but its ability to observe the earliest stages of galaxy formation was limited by its sensitivity and wavelength range. However, James Webb is designed to observe the faintest and most distant galaxies, providing direct evidence of their formation and evolution. Thus, in the first few months of its operation, the observatory has already made groundbreaking discoveries. For instance, it has identified galaxies that formed only a few 100 million years after the Big Bang, challenging previous models that suggested galaxy formation took longer to occur. These observations have prompted astronomers to reconsider their understanding of how galaxies form and evolve in the early universe. Webb data suggests that galaxy formation may have begun earlier and proceeded more rapidly than previously thought, which could have significant implications for our understanding of the conditions that existed in the early universe. Besides, the Webb telescope is also revolutionizing our understanding of star formation and the life cycle of stars. Star formation occurs in dense clouds of gas and dust, which absorb visible light and make it difficult for traditional telescopes to observe the process. Fortunately, infrared light can penetrate these clouds, allowing James Webb to peer into the heart of star-forming regions and observe the processes that give birth to stars. One of the most significant discoveries made by James Webb is the ability to observe the earliest stages of star formation. The telescope has captured images of protostars, which are in the process of forming from collapsing clouds of gas and dust. These observations provide crucial insights into the conditions required for star formation, the role of magnetic fields, and the impact of nearby stars on the formation process. Webb's ability to observe these early stages in unprecedented detail is helping astronomers to refine their models of star formation and understand the factors that influence the birth of stars. In addition to observing the birth of stars, James Webb is also providing new insights into the life cycle of stars, particularly the later stages of stellar evolution. The telescope has captured detailed images of planetary nebulae, which are the remnants of dying stars that have shed their outer layers. These images reveal complex structures and chemical compositions that were previously unknown, providing clues about the processes that occur as stars evolve and die. Furthermore, Webb's observations of supernova remnants are shedding light on the final stages of massive stars. By studying the remnants of these powerful explosions, astronomers can learn more about the elements produced in supernova and how they are dispersed into space, enriching the interstellar medium with the building blocks of new stars and planets. The data obtained by James Webb is helping to answer long-standing questions about the role of supernovae in the chemical evolution of galaxies and the universe as a whole. Another exciting aspect of the James Webb Space Telescope's mission is its potential to revolutionize the study of exoplanets and the search for life beyond Earth. Exoplanets, or planets that orbit stars outside our solar system, have been a major focus of astronomical research in recent years. The discovery of thousands of exoplanets by telescopes such as Kepler and TESS has raised fundamental questions about the diversity of planetary systems, the conditions required for habitability, and the potential for life elsewhere in the universe. James Webb is uniquely equipped to study exoplanets in unprecedented detail. Its infrared capabilities allow it to observe the atmospheres of exoplanets, detecting the presence of molecules such as water, carbon dioxide, and methane, which are potential indicators of habitability. By analyzing the spectra of light passing through an exoplanet's atmosphere, James Webb can determine its composition, temperature, and other key properties. One of the most significant achievements of James Webb in this area is its ability to characterize the atmospheres of Earth-sized exoplanets in the habitable zone of their parent stars. These are the planets most likely to harbor conditions suitable for life as we know it. Webb's observations of these planets could provide the first direct evidence of biosignatures, such as oxygen or ozone, in the atmosphere of an exoplanet, which would be a groundbreaking discovery in the search for extraterrestrial life. Moreover, the telescope is helping to answer questions about the diversity of planetary systems and the processes that lead to the formation of planets. By studying the protoplanetary disks around young stars, James Webb is providing insights into the conditions that give rise to different types of planets, from rocky Earth-like worlds to gas giants like Jupiter. These observations are crucial for understanding the factors that determine the composition and structure of planetary systems, as well as the potential for habitability in different environments. The James Webb Space Telescope is also contributing to our understanding of some of the most mysterious components of the universe: dark matter and dark energy. James Webb is not directly designed to detect dark matter or dark energy, but its observations are providing valuable data that can help to constrain their properties. By observing the distribution of galaxies and galaxy clusters, James Webb can provide insights into the effects of dark matter on the large-scale structure of the universe. The telescope's ability to observe distant galaxies with high precision allows astronomers to study the gravitational lensing effects caused by dark matter, which can reveal the distribution and properties of this elusive substance. After all, as you see, the discoveries made by the James Webb Space Telescope have prompted some cosmologists to question the validity of the LCDM model itself. While the model has been remarkably successful in explaining a wide range of observations, from the large-scale structure of the universe to the distribution of galaxies, it is clear that it may not be able to account for all of Webb's findings. One possibility is that the standard model needs to be modified to incorporate new physics. For example, some theorists have proposed that the properties of dark matter or dark energy may change over time, or that there may be additional, as yet undiscovered components of the universe that need to be included in the model. Others have suggested that our understanding of gravity itself may need to be revised, with alternative theories of gravity being considered as potential solutions to the problems posed by Webb's discoveries. Another possibility is that we may need to develop entirely new models of cosmology that can better account for the observations made by James Webb. This could involve rethinking the very nature of the universe, including its origins, evolution, and ultimate fate. Such a paradigm shift would be a major undertaking, requiring a re-evaluation of many of the assumptions that have guided cosmological research for decades. The crisis in cosmology sparked by the James Webb Space Telescope's discoveries is not limited to the field of cosmology itself. It has broader implications for other areas of astronomy and physics as well. For example, the unexpected findings about galaxy formation and black hole growth may have implications for our understanding of star formation, the interstellar medium, and the processes that drive the evolution of galaxies over time. Similarly, the challenges posed by Webb's observations to the Standard Model may lead to new insights into fundamental physics, including the nature of dark matter, dark energy, and gravity. The development of new cosmological models could also have implications for other areas of physics, such as particle physics and quantum mechanics, as researchers seek to develop a more complete and unified understanding of the universe. After all, the discoveries made by the James Webb Space Telescope have deepened the crisis in cosmology, challenging many of the assumptions and theories that have guided our understanding of the universe for decades. While this crisis may be unsettling, it also presents an opportunity for growth and discovery. As we grapple with the implications of Webb's findings, we may be on the cusp of a new era in cosmological exploration, one that could lead to a deeper and more profound understanding of the universe and our place within it. The crisis in cosmology is a reminder that science is a dynamic and ever-evolving endeavor. As new data becomes available and new ideas are proposed, our understanding of the universe will continue to change and evolve. The James Webb Space Telescope has opened a new window into the cosmos, revealing a universe that is more complex, mysterious, and awe-inspiring than we ever imagined. The challenges it has posed to our current theories are a testament to the power of scientific inquiry and the endless quest for knowledge that drives us to explore the unknown. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.
The James Webb Space Telescope is identifying objects in the dark ages that, by best measurements we have, are large, fully developed galaxies. So who ordered that?
For nearly all of the 20th century, the biggest question over the expanding universe had to do with understanding what its fate would be. The universe, if it's expanding, had to be a race between two seemingly irresistible factors: the initial expansion rate which worked to drive everything existing within the fabric of space mutually apart, and the force of gravitation, which fights against the expansion and works to pull everything back together again. Ever since the 1920s and 1930s, when the expanding universe became well established both theoretically and observationally, the primary quest of cosmology was to measure the present expansion rate as well as how it changed over time. Those two pieces of information together would allow us to infer the ultimate fate of the universe. Even after the Big Bang became established as our universe's beginning, scientists worked to improve these measurements, endeavoring to learn whether our cosmic expansion would eventually reversian recollapse, whether it would coast and continue to expand forever, or whether it would be right on the border between those two cases. The critical observations at last came in during the 1990s, determining that the answer was none of these options. Instead, the universe's expansion is accelerating, implying that a novel form of energy, dark energy, has come to dominate our expansion. It also implies that the universe we can observe is disappearing from our reach, and most of it is already gone. This idea is strongly supported by the surprising data obtained from James Webb. For little more than 2 years in space, NASA's $10 billion proves it's worth every penny. Historically, our grandest views of deep space came from Hubble. But as of July 2022, James Webb takes us beyond what anything else has seen. From the faintest galaxies to the richest clusters, to mostly empty cosmic voids, to the deepest depths of far-off space, and much, much more, the superior telescope has revealed details we've never seen before. Beyond all expectations, when James Webb focused on large regions of space that appeared blank to Hubble's eyes, it detected something mind-boggling. 900 trillion stars have mysteriously vanished into the void of space, and things are getting scarier by the minute. What happened? Where did stars go? How did they utterly go without a trace? Join us as we dig deeper into the shocking discovery made by James Webb, how Webb reveals details we've never seen before, and how the disappearance of that many stars might affect our planet as well as our very future. First off, accept that. James Webb outperforms Hubble by more than we expected. And when you look at the capabilities of James Webb and Hubble side by side, you would expect that our newest space telescope could do much more in less time. Whereas Hubble has a primary mirror that's 2.4 meters across, Webb's segmented mirror spans 6.5 meters. This leads to a resolution that's 270% as sharp for the same wavelength light, and light-gathering power that's 730% as great as Hubble's. From the physics of optics alone, that's how much better and faster James Webb should be than Hubble, not including the advantages James Webb also possesses in terms of cooling, wavelength coverage, and instrumentation. In other words, for the same amount of observing time, you'd expect that James Webb would collect 730% as much light as Hubble. But James Webb, as you can see in the comparison of its composite image of galaxy cluster SMACS 0723 with that of Hubble, is doing even better than that. Hubble time is divided up into orbits, as from its position in low Earth orbit, it completes a revolution around our planet every 96 minutes. A total of 6 orbits, 4 in optical wavelengths and 2 in infrared wavelengths, were used to make the Hubble composite. You'd expect, based on simple math, that 6 orbits multiplied by 96 minutes per orbit would equal 9.6 hours, or 576 minutes of Hubble time. But there's only a total of 3.4 hours, or 203 minutes, of Hubble data that's gone into these images, despite nearly 3 times as much of Hubble's time having been devoted to this target. For comparison, James Webb observed this target for 12.5 hours and got 12.5 hours worth of data. What's the difference? Location. Hubble, because it's in orbit around Earth, spends more than 50% of its time with the Earth and the Earth's atmosphere, in the way of its desired target, and can only acquire useful data when its target is in full, unobstructed view of the telescope. Meanwhile, James Webb is some 1.5 million kilometers away at the L2 Lagrange point. It always faces away from the sun, away from the Earth, and away from the moon. It never has to contend with these obstacles to pristine observing, and so its observations of targets are 100% time efficient, as opposed to less than 50% time efficient like Hubble was. This improved efficiency extends to all observations taken with James Webb and should enable faster, better science than Hubble could ever achieve. In other words, James Webb gave us the proof we needed. Not only can James Webb find the objects that appeared blank to Hubble's eyes, in many cases, it can resolve them and examine their properties, whereas Hubble could not even see them at all. This helps us achieve one of James Webb's main science goals: to teach us, in the goriest details possible, how the universe around us grew up and came to be the way it is today. For instance, nearby, Jupiter appears as never before. Its bands, rings, aurorae, and moons appear alongside background galaxies. James Webb viewed exoplanets directly with infrared imaging. Spectroscopically, transits detect absorbed light and transmitted light, revealing molecular presences. Star-forming nebulae display unprecedented details. From new young blue stars to gaseous features, James Webb showcases what Hubble cannot. Meanwhile, Webb's initial alignment image grew spectacularly. Now a 140-plus megapixel view, it expansively reveals far-flung galaxies. Just 1% of this view contains 100 identifiable objects. Massive, evolved, complex galactic shapes appear at all observed distances. Additionally, disk galaxy candidates surprisingly appeared at extremely early times. James Webb also viewed the most distant star ever, Earendel. But arguably, its greatest images are of individual galaxies. Webb's views reveal gas, dust, stars, and more. Central black hole containing cores shine in mid-infrared light. Star-forming gas bridges appear between interacting galaxies. From Hubble to James Webb's near-infrared eyes, to the eerie, unfamiliar mid-infrared views, the universe is coming into focus as never before under Webb's watchful eyes. But in a shocking observation, James Webb has detected trillions of stars disappearing without a trace. But how? Where did they go? The two leading theories about what happened are that either it's still there, still erupting its way through its death throes with less luminosity and perhaps obscured by dust, or it just up and collapsed into a black hole without going through a supernova stage. But in the worst-case scenario, the universe is just disappearing, and we're powerless to stop it. To understand the dilemma, a brief refresher is needed. At the start of the hot Big Bang, the universe was rapidly expanding and cooling, while individual clumps within it were also gravitating. Over time, the expansion rate slowed and the temperature dropped, leading to the formation of stable bound structures for the first time. After about a microsecond had elapsed, protons and neutrons formed. After another few minutes, the first stable atomic nuclei were forged. Hundreds of thousands of years later, neutral atoms came into existence. And after tens to hundreds of millions of years, the first stars and galaxies came into being, all while the expansion rate dropped and dropped. For the first several billion years of cosmic history, this appeared to be precisely what was going on. The universe began expanding, but the gravitational effects of matter and radiation worked to pull things back together, slowing the expansion rate down. Objects that were farther and farther away appeared to recede slower and slower as time went on, and the light emitted by once invisible objects, far beyond the cosmic horizon, finally caught up to us, the observer. More and more of the universe came into view. And then, about 6 billion years ago, the matter density dropped by such a significant amount that dark energy's effects began to become important, and everything changed. Prior to this moment, if you had put your finger down on any distant galaxy, you would have seen that it receded from us, getting farther and farther away as time went on. However, if you measured its recession speed from us, i.e., how much its light was redshifted by the expansion of the space between that galaxy and ourselves, you would have observed that to decrease with cosmic time. Even as it moved farther away from us, the expansion rate of the universe dropped by a more significant amount, ensuring that although it still appeared to recede, it was receding slower than it was previously. This allowed the light emitted from objects at even greater distances to catch up to us over time, bringing them into view. However, at an age of about 7.8 billion years, or about 6 billion years ago, all of that changed. Objects at all distances, greater than about 5 million light-years away, that is everything beyond the local group that's gravitationally bound to our own galaxy, began receding from us faster than they had been previously. Fewer and fewer new objects would now come into view as they began accelerating away from us. The objects that were beyond a certain critical distance would remain visible, but we'd only be able to see the light they emitted in the past, not the light they're emitting today. Additionally, we'd be unable to reach them, either by spacecraft or with a light signal, even if we sent it right now. Only the closest objects would remain both visible and reachable, creating 4 distinct regions to our observable universe. Based on their present distance from us today, 13.8 billion years after the Big Bang in the dark energy-dominated era, we can classify the 4 regions that describe the objects within our universe. First, observable and reachable. If an object, at present, is closer than about 18 billion light-years away, we can both see it and reach it. If we sent a signal to a galaxy within this distance, even today, it would be able to reach that galaxy. And if we embarked on a journey to reach that object, we could reach it even at sublight speeds. Second, observable, but not reachable. If an object is more than 18 billion light-years away, but closer than 46 billion light-years away, it's still observable by us, but only as it was in the past. It can see us as we were in the past, but we cannot reach it in any way, not by spacecraft and not with a light signal. We are only connected to these objects in the past. Third, observable, but only in the future. If an object is more than 46 billion light-years away, its light will not have reached us yet within the expanding universe. However, if that object is also closer than 61 billion light-years away, the light it emitted long ago is already on the way and will reach us at some point in the future. Although we can only see it as it was in the distant past, at some point it will become visible to us. And last, forever unobservable. And beyond a distance of 61 billion light-years, no object will ever be visible to us or reachable by us. This is profound and remains unappreciated by most. Even though 18 billion light-years is 39% of the way to the edge of the observable universe, a seemingly impressive and substantial number, we live in 3 spatial dimensions. 3. 9% of the way to the edge of the observable universe in one dimension represents only 6% of the volume of the presently observable universe. In other words, even though there may be between 6 trillion and 20 trillion galaxies contained within the observable universe, only about 6% of them, the closest 6%, are presently reachable by us. The remaining 94% can only be seen as they were in the past. There are almost certainly galaxies beyond the limits of our presently observable universe, as we have every indication that beyond that boundary simply lies more universe as we know it. But their light hasn't yet reached us. Although 61 billion light-years isn't that much larger of a figure than 46 billion light-years, it encapsulates an extra 133% of the volume presently contained in the portion we can see right now. There are more than twice as many galaxies that have never been observed that will someday become visible to our instruments than are in the presently observable universe today. Even though the universe keeps on expanding, eventually, that light, although red-shifted severely, will catch up to us. However, it's important to remember that this picture provides a mere snapshot of our existence at present. In reality, the matter and radiation densities are continuing to drop. The dark energy density is remaining constant, and the expansion rate, measured in kilometer per second per megaparsec, isn't dropping to zero, but is asymptoting to a positive, finite value. It's this last part that's extremely important. In any expanding universe in the context of general relativity, there's a relationship between the rate of expansion, also called the Hubble parameter, at any moment in time, and the square root of the total energy density from all forms, including matter, radiation, and dark energy. Right now, the expansion rate is, depending on which set of measurements you believe is more correct, either 67 kilometers per second per megaparsec or 74 kilometers per second per megaparsec. This means, for every megaparsec, or about 3.26 million light-years, that an object is distant from us, we see it receding from us by either 67 kilometers per second or 74 kilometers per second, meaning that objects that are 10 megaparsecs away recede at 10 times that speed. Objects that are 100 megaparsecs away recede at 100 times that speed, and so on. However, because the expansion rate is dropping, but only to about 82% of its present value, that means in the future, the expansion rate will asymptote to either 55 kilometers per second per megaparsec or 60 kilometers per second per megaparsec, or somewhere in between if that's where the true figure lies. Because of the enduring presence of dark energy, that doesn't just mean that 94% of the galaxies within the observable universe have already disappeared to be beyond our reach. It means that the universe is in the process of disappearing beyond our reach, and that while 94% of them have already crossed that milestone, the other 6% of them, including every single galaxy that isn't a part of our local group, are already in the process of disappearing. There are about 2 sextillion stars clustered into those trillions of galaxies contained within the observable universe, but only 6% of them, or around 120 quintillion of them, are presently reachable today. With each new year that elapses, hundreds of millions of additional stars cross over that threshold, from being reachable to being unreachable, corresponding not to a handful of small galaxies, but rather to portions of perhaps hundreds of galaxies, both large and small varieties. On extremely long cosmic timescales, however, these changes can be tremendous. After another billion years has elapsed, or just bog 7% of the present age of the universe, the percentage of the observable universe that's still reachable will have dropped by another enormous step, from 6% to 5%. That means just 1 billion years from now, after the last total solar eclipse has occurred on Earth, but perhaps even before the sun heats up sufficiently to boil our oceans, we will only be able to reach 100 quintillion stars, having lost another 20 quintillion, between 300 billion and 1 trillion galaxies, having now lost 95% of the total galaxies in the universe, and the galaxies that are presently located within the 16.7 billion light-years from us, having lost every object presently between 16.7 billion and 18.0 billion light-years away. We can go a little bit farther if we dare. Another 5.2 billion years ahead after that, further 1 billion years. At that point, the Milky Way and Andromeda galaxies will have begun merging, and the Sun should be transitioning into a red giant, where it will swallow Mercury, Venus, and possibly the Earth as well. And at that point, we'll only be able to reach fewer than 2%, about 1.75%, of the stars and galaxies within our presently observable universe, corresponding to just 35 quintillion stars, and between 105–350 billion galaxies. In the meantime, what we presently call Laniakea, our local supercluster, will have already begun visibly dissociating into its component groups and clusters, being driven apart by dark energy. It isn't just the most remote galaxies that expand away from us, being driven to greater and greater distances by dark energy. It's every galaxy that isn't gravitationally bound in the same group or cluster as our own. After roughly 63 billion years have passed by, all 100,000 galaxies that compose what is known as Laniakea today will be the only galaxies that are reachable by someone living in the local group. There will be around 100 quadrillion stars inside these galaxies, but many mergers will have occurred, leaving the number of galaxies a much smaller number than are present within Laniakea today. Over the following few billion years, the large clusters within Laniakea, things like Norma, Centaurus, Hydra, and Fornax, will recede beyond the reachability limit. The Great Virgo cluster of galaxies, only 55 million light-years away at present, and consisting of over 1,000 member galaxies, will become unreachable just before we reach the 100 billion year milestone after the Big Bang. And what are presently the closest galaxy groups outside of the local group, objects like the M81 group, will be the last to become unreachable, something that won't occur until more than 110 billion years from now, when the universe is nearly 10 times its present age. Nearly 100 years ago, we began collecting the first evidence for the expanding universe, and with it, the first evidence of our cosmic origins, the original notion of the Big Bang. Once we began seeing very far back in cosmic history, not just millions or hundreds of millions of years back in time, but several billion years, we began to investigate not only our cosmic origins, but our cosmic fate as well. And what we found, to the surprise of many, was that our universe couldn't, but rather was dominated by a mysterious form of energy that was driving all gravitationally unbound structures apart: dark energy. Dark energy doesn't just determine the fate of the universe, it also determines the distance and time scales on which galaxies, galaxy groups, and galaxy clusters would all fly apart from one another. Today, 13.8 billion years after the Big Bang, we can see up to 46 billion light-years away, but only 6% of the volume of our observable universe can be reached by us. As time continues to progress forward, the amount of the visible universe that we can see will continue to increase, but the galaxies within the portion of the universe that's reachable will continue to decrease as they all move farther and farther away from one another. At last, after another 112 billion years pass by, the final galaxies beyond our local group, representing the closest galaxies to our own local group today, will finally recede beyond the reachability limit, receding too fast for even light to catch up to it. No restriction on the amount of time that can pass, then all of these occurrences are simply inevitable. The only question is when. Which brings us to an important question. If you're going to trigger a nuclear fission reaction with the Big Rip scenario, where the subatomic particles at the heart of each atom's nucleus are ripped apart into their constituent components, how much time do we have for that explosion to propagate throughout space before the universe itself ends? For nuclear explosions, the propagation time can be devastatingly fast. The above high-speed photographic sequence shows one of the original test detonations of an early atomic bomb in the 1940s, and you can see that in mere milliseconds, the explosion has expanded to take up a volume that's larger than the size of a football field, over 100 meters across. It's a rapidly expanding explosion resulting from a tremendous release of energy, but it's still slow, less than 1% of the cosmic propagation limit set by the speed of light. Unfortunately, by the time atoms and atomic nuclei themselves get torn apart, we're only 10^19 seconds away from the end of the universe. Even if the released energy traveled outwards at the speed of light, it would only travel about a third of an angstrom through space before the universe came to an end. This comes as a disappointment to most people. Sure, it's fascinating to think about alternative fates to the mainstream for our universe, but that requires something exotic. That dark energy be something even more bizarre and mysterious than is commonly thought. While either the cosmological constant or the zero-point energy of the quantum vacuum can be folded into our current theories without adding anything novel, Something that causes dark energy to strengthen over time would require some type of new field, particle, or interaction. However, once you're willing to invoke such an entity, a number of fascinating possibilities for the fate of the universe suddenly arise. They include the universe spontaneously transitioning to a lower energy state, looking very much like a repeat of the end of inflation that kicked off the hot Big Bang, the act of tearing space apart, resulting in a sort of reverse singularity, where space and time can either be reborn or can disappear into nothingness, or the universe actually undergoing a cyclic phenomenon, where a closed time-like loop ensures that the universe plays again on repeat, just as it did before, except with the quantum outcomes of various interactions being no more predetermined than they were in this iteration of the universe. The Big Rip is one possibility for how the universe could end, but if dark energy increases with time, we have to face the facts. At some point, we're going to have to deal with energies and temperatures that are high enough that we've never explored them. In those regimes, anything that's not ruled out remains possible. Simply put, the universe is disappearing, and we're absolutely powerless to stop it. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you